Hey, grade 12s. Today we are going to be graphing sinusoidal functions. And again, we're going to be looking at some familiar diagrams that we have seen already a couple times in this unit. First off, we take a look at the graph of y equals sine x. And on this graph of y equals sine x, the standard function, we start on the midline, and after 1/4 of the period, we reach the maximum. Then at 1/2 of the period, we go back down to the midline. At 3/4 of the period, we go to the minimum. And after 1 full period, we're back up to the midline. As mentioned in a previous lesson, previous provincial exams have not had any real involvement with the cosine of x. So we will not have any involvement with cosine of x, but here is the graph if you'd like to look at it, and if you'd like to mess around with it, you can, but we're not going to spend any time talking about it. Again, we've also seen this before too. A sinusoidal function is of the form y equals a sine b bracket x minus c plus d. And the same formula with cosine in it as well. And we talked about A being the amplitude, B influencing the period. Specifically, the period is equal to 2 pi over B. And if we need to use the other form of that formula, if we rearrange it, it's also B is equal to 2 pi over the period. That's just a rearrangement of the first formula. When we talk about C, it influences the horizontal position. The mathematical term for that is phase shift. And the other term that we threw around the other day was a translation. It moves the graph left or right. It may mean that the starting point is not on the midline, or more specifically, it's not on the midline and heading up. And A does talk about the amplitude, if we go back to that, but it also talks about stretching and compression. And more notably, it talks about vertical stretching and compression. Whereas B, which has a lot to do with what the period is, B, and I won't write this down because I'm kind of short on space, but B is horizontal stretches or compressions of the graph. And D is the median line, so that would be a vertical translation, either up or down. And in either case of sine x or cosine x, the period is 2 pi. And again, we're only talking about sine x, so that's all we will concern ourselves with here. So let's get down to business. Here we go. Let's graph at least one period of 10 sine x plus 4. Now, in these examples, and I see there is an example with cosine for part B, we'll ignore that question. We will, in fact, if there's any other cosine ones, which I expect that there probably will be, no, there's only one with cosine. And we're going to ignore that because we don't have to worry about cosine. The homework assignment may even have cosine in it, but again, Does it? Oh yeah, it has cosine on maybe a couple of them. And again, we'll ignore cosine because again, we don't have to consider cosine, so we won't. So we're looking at one period of 10 sine x plus 4. So what we really want to know is which of those parameters, A, B, C, or D, are different. Well, the 10 is the A value, and the 4 is the D value. And just as I mentioned last class, A and D are the easiest to work with. So we're okay here. And what we'll do is we'll look at D first. D is the median line or the midline, and it's at 4. It's also given that the amplitude is 10. So that means the graph is going to go 10 units up and 10 units down from 4. So in other words, the maximum will be at 14 and the minimum will be at -6. So our graph must accommodate those y values. So for that reason, what I should probably do is do this. Doesn't really matter how we do this. I don't think it's going to be great either way. 2, 4, 6, 8, 10. That's not enough. It's 12. We're going up to 14. So we might as well make this worth 4. So that's 8, 12. No, apparently I forgot how to do math. That's 16. That's 24. That's -8, -16, -24. So that's our vertical scale. A and D actually only affect the vertical scale. So that means the horizontal scale remains intact. Well, that's nice. But before we talk about horizontal scale, let's remember that the midline is at 4. So that means our first point will be right on the midline. Now we have to define our scale for our x-axis. One period goes up to 2 pi. How many grid squares do we have? 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18. Is that right? Okay, 18. I don't know if I really like 18, but I'm the one that did it, so no one to complain to except for myself. There's 2 pi. We'll put 2 pi after 16 grid squares. Then what that really means is that after 4 grid squares, that's pi over 2. After 8 grid squares, that's 1 whole pi. After 12 grid squares, that's 3 pi over 2. And 16 grid squares will be 2 pi. Now we have a scale on both the x and the y axis. Yeah, half pi or pi over 2 is our first point on the x-axis. 1 whole pi comes at 8 grid squares. 3 pi over 2 is at 12 grid squares, and 2 pi is at 16 grid squares. So the amplitude is 10, so that means we're going up to 14. Now 14 would be right here, halfway up to 16. What was the question? -6. -6. We take the midline and add the amplitude to get the maximum value. We take the midline and subtract the amplitude to give us our minimum value. And that helps us plan out what our y-axis should be like. We need to cover all values from -6 to 14. Now at pi, we'll be back at the midline. At 3 pi over 2, we're going to be at -6, which is right here. And then at 2 pi, we're back at the midline. So it's not going to look too crazy. It'll look something like this. I already kind of blew it. It's kind of what we're looking for there. Now, if you pick a slightly different scale for your x or your y axis, the graph will also take on a slightly different look. But that is what one graph of, or one period of 10 sine x plus 4 will look like. 10 being the amplitude, the a value, 4 being the midline, which is the d value. We don't have to worry about the period being anything different than 2 pi, and we don't have to worry about any kind of phase shifting. Yes. Right, it's a curve. Yeah, it is a curve. I didn't draw the curve with a great amount of finesse, but I've drawn a lot worse curves, so I'm okay with that. Okay, we are skipping the next question because we don't care about cosine. But we are going to do this next question and the two questions that follow it. So we're graphing at least one period of 2 sine bracket 2x minus pi minus 3. I'm okay with that. So the problem with this expression is it's different than this expression right here. There is a distinct difference. Here, the b is factored out. It's factored out of this. So what we need to do is we need to factor the 2 out of that. So that means that we're going to have 2 bracket x minus pi over 2. Everything else is the same. So what does that really mean? It means that your c value is not pi. That's what it means. A is 2, b is 2, c is pi over 2, and d is -3. So you have to do a little bit of algebra. You have to take out a common factor of 2, and you always have to take out whatever number's in front of the x as a common factor, because we always have to have x minus or x plus something in that bracket. So here we go. Let's start with d. D is -3, and a is 2. What does that mean? Well, what that means is the maximum value is going to be -3 plus 2, and that's -1. That's going to be the maximum value. The minimum value is -3 minus 2, and that is going to be -5. So if the maximum value is -1, then it would stand to reason that this graph will never go above the x-axis. So as far as the scale goes, well, we have to go to at least -5 And we have 6 grid squares going in up or down in either direction. So we could probably just make every grid square worth 1. And then by doing that, we get something like this. 0, 2, 4, 6, and 0, -2, -4, and -6. As far as the x-axis goes, the period is 2 pi divided by b. Well, b is 2. So the period is 2 pi divided by 2. So the period is plain old pi. So that means that our x scale has to go up to at least pi. Now, so if we want to go up to at least pi, well, why don't I just make pi right here at 16 grid squares again? That's pi. After 8 grid squares, we'll have half of that, or pi over 2. After 4 grid squares, we'll have pi over 4. And at 12 grid squares, we'll have 3/4 pi, or 3 pi over 4. To do this question, what I would do is I'd assume it this way. I know that the regular sine curve starts right here. Then it goes up to the maximum, comes back down, goes to the minimum, and then comes back up. Now, why I'm doing that and why I'm looking at that is this. We know that's going to look like this, come back down, then come back up. And usually, if there's no kind of phase shift, this would be the beginning, this would be the end, so this would be 1 whole pi. This halfway point will be the pi over 2. This will be pi over 4. And this will be 3 pi over 4. But because we have something in this expression, this right here, this minus pi over 2, what that means is we move everything pi over 2 to the right. Everything moves to the right, pi over 2. So let's look at this grid. To get to pi over 2, how many grid squares do we have to go? 8. So that means that these points are going to move 8 grid squares to the right. So if we would have started on the axis is -3. So if we would have started right here on the axis, we're now moving 8 grid squares to the right. 1, 2, 3, 4, 5, 6, 7, 8. So that beginning point that would have been way over at the beginning is now right here under the pi over 2. After the beginning point, we go to the maximum. And the maximum would have occurred at pi over 4. And according to what we have over here, the maximum value is -1. So the maximum value would live right where my marker is pointing right now. But we're not going to be putting the maximum value there because we're moving 8 grid squares to the right. So 1, 2, 3, 4, 5, 6, 7, 8. We see a new point right here. That is where the maximum is going to occur. The next point is right on the median line or the midline. So it's going to come back down to -3. So that point would have occurred at pi over 2, but it's going to be moved over 8 grid squares to the right. 1, 2, 3, 4, 5, 6, 7, 8. So what we have is 3 points drawn. Now, I understand that if we look at the black curve over here, there's 5 dots. So what we need to do is we need to backfill the last piece of this to make one complete cycle or one complete period. So if we kind of look at the shape this is going, we see that it's going like this. It's going to come up and it's going to come down. What's going to happen over here at pi over 4? It's going to go to -5. That's right. So I'm going to kind of MacGyver this curve a little bit. Oh, I don't want to do that. I don't want my highlighter. Okay. Good. And now, what will it be at the very beginning? What's the y value going to be at the very beginning? -3. So this graph still starts on the median or the midline, but instead of heading up, as we've always seen so far, the graph heads down. Then it comes back up to the midline, goes up to the maximum, and comes back down to the midline. And that's because of that pi over 2 that represents the C value. Now I want to show you something with Desmos that's going to back up what I just did. So let me open up Desmos here. Okay. Okay, pausing so people can get everything written down. Okay. All right. Now, going to Desmos. I'm going to type in an equation that's very similar to the one we just did, except one exception. It's not going to have that bit in the bracket. It's going to have 2 sine bracket 2. Now you can just watch. X plus a minus 3. Okay, so this is what the graph would look like, but I just want to set up the scale so it looks reasonable. I want to go from, say, negative pi to 3 pi, and I want to go from negative 6 to 2. And we're going to go up by pi over 2's. And I don't even have to go that far. I'm going to go 2 pi, sorry. And I'm going to go pi over 2 here. Now, you know what? I'm just even going to pi. Going to really kind of shake things up here. Okay. So we take a look at this graph here. I want you to pay special attention to this. My cursor is at negative 3. This is how we're used to the sine curve doing its magic. It's going to go up, start up, go up to the maximum, negative 1, come back down to negative 3, go all the way down to the minimum, and then come all the way back up to the midline. That's how we're used to this graph happening. But what we have to do here is we have to go ahead and we have to go pi over 2. So what I'm going to do is I'm going to go pi, and I'm going to go pi over 4. What I want you to do is I want you to see something. If we shifted this graph pi over 4 to the right, then that's what it looks like. It starts at the bottom, comes up to the midline, comes up to negative 1, goes back down to the midline, and goes all the way down. Now, we didn't add pi over 4, we added pi over 2. So when we have pi over 2, we have this. Starts at negative 3, goes down to negative 5, up to negative 3, and then up to negative 1, and then back down to negative 3. This is what our graph that we just did looks like. So we can see that if there's no phase shift, it looks like the traditional sine curve. It starts on the midline, goes high, comes low, goes all the way low, and comes back to the midline. But because we're shifting it pi over 2 units to the right, it actually physically moves the graph to the right. And I understand that right's this way for you guys. It moves it to the right, pi over 2 units. So what I always do myself as I think of those 5 key points, I think of this point right here at the beginning. I think of the quarter point, which is at the maximum. I think of the halfway point, which is back down at the midline. It's not going to highlight it, but you understand what I'm doing. I think of the 3/4 point, which goes back down to the minimum. And I think of the full point, which goes back to the midline. I think of those 5 key points. And if we take those 5 key points like we did when we did that example, and we move those 5 key points pi over 2 units to the right, then all we have to do is connect the dots and we get the curve. And this stuff does take a little bit of time. It takes practice. When we are fiddling around with phase shifts or moving graphs left or right, that's when these questions are at their nastiest. Okay, so if you can get this stuff, you are a rock star. Okay, now, how many more examples? 2 more examples. Here we go. Here's another one. Graph at least one period of 10 sine bracket 1/2 x minus 3 pi over 2 plus 3. So again, we're going to have to take out a common factor of a half just to figure out what the real phase shift is going to be. So we can do that, no problem. If we take out half here, then if you divide by half, it's like multiplying by 2. So 3 pi over 2 just becomes 3 pi. So this is what the equation becomes like. So if you are given an equation, we are factoring out the b value here. If the b value is already factored out, then giddy up. You've got nothing to do. But if the b value is not factored out, then you need to factor it out before you go ahead and graph this. Once again, though, how we do this is we always start with our d and our a values. What is d? What's d? 3. Okay. And what's a? So it means that 3, if we add 10, we get 13. That'll be the max. If we subtract 10, we get -7. That'll be the minimum. So we have to pick a vertical scale that at least will cover all values from -7 to 13. Well, to do that effectively, we can make every grid square worth 3, I guess. I don't know how great that is, but we can work with that, I guess. So this is 6, 12, 18, -6, -12, -18. If d is 3, we can do this. It doesn't hurt anything. We just have to be gentle. We can draw a light dotted line at -3 just to kind of give us the reminder that that's our midline, that's our median. What's our b value in this equation? Half. So this is kind of goofy, but to find the period, we take 2 pi and divide it by half. Now, before you kind of rack your brain trying to figure out what that is, all you have to think of it this way is if you have 2 pizzas and everyone has half a pizza, how many people can eat the pizzas? You've got 2 pizzas, and you want people to have half a pizza each. 4 people can eat, right? There's 4 halves in 2. There's 4 halves in 2, so it's 4 pi. So 4 pi is our period. So that means we must go to at least 4 pi. So hey, why don't we go up to 4 pi here at 16 grid squares? And really, as long as you make, like there's basically 4 intervals here. And I'm doing it so that every interval is 4 grid squares. As long as every interval is the same number of grid squares, it's fine. But you should try to use all the grid squares you can. I did make some very nice, pretty blank graphs for you so you can do this where the grid squares are set up a little differently, but it does give you the freedom of choosing how you want to set it up. So we know that we're going to be putting a little tick at 4 grid squares. We know we're going to be putting a tick at 8 grid squares. We know we're going to be putting a tick at 12 grid squares. So how many pi are here where my pointer is pointing? That's 2 pi, that's right. And how many are where my pointer is pointing now? 1 pi. And how many pi's are right here? 3 pi's. 1 pi is a quarter of 4 pi. 2 pi is half of 2 pi. And 3 pi is 3/4 of 4 pi. So that's how we get those numbers. Now we can start plotting some points. But before we get too fired up with that, we have to think about what that C value is. That C value is 3 pi. So that means we move everything to the right 3 pi. So if we would start on the median line right here, don't put a dot here, but this is where we would typically start. What we have to do is we have to move 3 pi to the right, okay? So that point doesn't really go there, it goes here. And at the quarter point, we know we'd go up to our maximum. Yes, Malcolm? Good catch, Malcolm. Very good catch, Malcolm. Thank you for that. Malcolm with a very good catch. Come on. Come on. There we go. Thank you, Malcolm. So we'll go through that again. Technology makes us this, so it's not too bad. Again, I'm not really going to put a dot here, but I'll put a dot here temporarily. We're moving that dot 3 pi to the right. So that dot goes right here. Now at the quarter point, we would be at the maximum. The maximum is 13. Well, that's going to be like right here. Now, I am going to draw this one in because you're going to see what I'm going to do. I just thought of this, being clever like I am. What we can do is we could take that point and move it 3 pi to the right. So what's pi plus 3 pi? 4 pi. So it's going to be, it's just moving right. It's not moving up or down. It's just moving to the right to 4 pi. So now the point is right there. So what we have to understand, and I understand that we only have part of this graph drawn, but this is the part of the graph where we start and then go up to the maximum. We start and then we go up to the maximum. So that part of the graph looks like this. If we're drawing one complete period of this, we have to go back and backfill this to the left of 3 pi. So what's the graph going to do from 3 pi to 2 pi? Go down to what y value? -7, the minimum. And -7 would live like right here. So it's going to go down, 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 boom. There it is. Right there, -7. And then what's going to happen as we move from 2 pi back to pi? It's going to go back to the midline, which is right here. So we're going to go up, 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 stop. So stop on the midline. And now where's it going to go from pi all the way back to the beginning? What's that? What'd you say, Sky? 13, and you said? You said 13, and you're right. It goes back up to 13, which is like right here. So my graph isn't perfect because my smartboard isn't perfectly aligned, but your graph should look something like this. Okay? So understand that when we do this, we definitely start with what that D value is. We use that A value next to find out our possible Y values. Then we figure out our scales using those D and the A values plus your B values, and then we use the C values to move stuff around. One last question.
Tasha Dion to the school office, please. Tasha Dion to the school office.
Graph at least one period of each of the following sinusoidal functions. Hey, listen, this is a bonus question. I mean, not this one, but I'm going to tell you something. This is a bonus question I'm going to tell you about here. So you can just pay attention to this, what I'm going to show you here. Because it's just something I want to let you know. Okay. And we'll just do something simple here. No. Yeah. We are. We're going to do the last question. I want to show you what y equals sine x looks like. And sine x is not any kind of weird animal. We've looked at this over the last several days. This is not very unfamiliar. I mean, it is a little bit unfamiliar because you've never kind of done stuff like this before. But the graph of sine x, of course, starts at 0. It goes up to the max, comes back down to the midline, goes back down to the minimum, which I guess is kind of like right here, and then back to the midline. So like this, like this, like this, like this, and then like that. That's what sine x looks like, okay? A nice, beautifully drawn graph of sine x. Now, in some of the questions for homework, you're going to get something that looks like this. And there might be other numbers with it, but you might be asked to draw this. Negative sine x. Now, what in the world do we do with negative sine x? Well, what do you think, Malcolm? Malcolm thinks you flip the graph. And you flip the graph in which direction, though? Vertically. Malcolm says we flip the graph vertically. Malcolm is correct. Because if you remember way back when we had something like this was our x squared. But then if we thought about what negative x squared was, it was flipped vertically, and that's why that's the case. So if we have negative sine x, then we would still start wherever the median line would be. Actually, that's not necessarily true. If the median line was positive, we go to the negative one. So really what we do is we flip it in the x-axis. Flip it in the x-axis. So if points are on the x-axis, they don't move. But if points are above the x-axis, such as this point here, well, then it goes down here. And if points are below the x-axis, like this one here, well, then it flips up here. So y equals a negative sine x looks like this. Exact same type of shape, except it's flipped upside down. So if you get negative sine x to deal with, your base shape is not going to be the blue shape that we've come to know and love. Your base shape will be the red shape. Instead of heading up to the maximum first, it's going to go down to the minimum. Okay? So keep that in mind when you go through questions in the homework. Now, we do have one more question to do. Let's do it. One period of this. So we'll start off with D. D is negative 110. A is 250. And we don't have to worry about factoring out the B because the B is already factored out, which is nice. So the maximum value is going to be 140. The minimum is going to be negative 360. That's our max, that's our min. So we should build our vertical axis to reflect those values. So I'd say as long as we hit 400, we're laughing. Okay, there's 10 grid squares. Let every grid square represent 40. So this would be 80, 160, 240, 320, 400, negative 80, negative 160, negative 240, negative 320, and negative 400. Okay? That's a vertical scale we can live with because it touches on all the values that we have in the question. As far as the scale goes, a horizontal scale, things get a little bit more funky because the b value is 2 pi over 60. So what we have to do is we have to take 2 pi and divide it by 2 pi over 60. So how do we do that? How do we do that? Well, if your b value is ever pi divided by something or 2 pi divided by something, that's a very good indication that your period is going to have nothing to do with pi. And what we actually do is the same treatment as when we multiply or divide fractions. When we divide fractions, we change the sign to multiplication and we flip it upside down. And then what we get is a period of 60 units. 60 units. That's our period. There's no attachment or association with pi. Our period is 60 units. So that's our horizontal scale must go up to at least 60. Nothing to do with pi. So if we did a question like the Ferris wheel question, we'd expect the b value something like this. When we talk about seconds and minutes and stuff, we're not talking about pies or half pies or whatever. So here we go. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We still have 18. So I'm going to put 60 right here. And that means that means that this is 30. This is 15, and that's 45. We've got 1/4, 1/2, and 3/4 of a period, all labeled on the x-axis. And now we are almost ready to start plotting points. Okay? So our d value is -110. We could put it's not going to be exact. It's going to be just above, and it's a little bit more above than I managed to put it. So I'm just going to adjust this. It's going to be like maybe about right here. Almost 1 grid square, not quite. Almost 1 grid square below the 80, but not quite. That's where the 110 is going to live. It's 3/4 of a grid square. And from that, we should be able to start plotting our points. Now, what we have to understand is if this was a standard graph, and it's not a standard graph with no phase shift because of this. The interesting thing is it's plus 15, which means instead of moving right, we're going to move left. We'll talk about that in a minute. I'm going to plot what the points would be with no phase shift. And you don't have to write them down, just watch. We would start here at the grid line, at the midline. The maximum is 140, so we'd go up to that maximum of 140, and it would be right here. And then we go back to the midline at the halfway point. We go down to the minimum right here, and then we come back up to the midline right there. But the interesting thing about this is instead of moving our points to the right, we're moving our points to the left. And we're moving our points to the left 15 spots. So the one that's at 0, hate to say it, but we don't really care about it anymore. It's gone. But the one at 15 will go to what value? What x value? If we're moving this 15 to the left, what's the x value now? What's that? No. If we're moving it 15 to the left, what's 0? That's right. So it's just going to go to the left right to here. Here, we were at the old halfway point, and we're moving it 15 to the left. So where do we go? We go to 15. Here, we were at the 3/4 point. We move 15 to the left. Where do we go? 30. And here, we are at the end, but now we're not because we have to move 15 to the left. Where do we go? What's that? Thank you. But in doing all those movements, we are missing a point. Where will we put a point at 60? What's that? Thank you, thank you, thank you, thank you, thank you. We go back up to the maximum. It's right here. So we're going to draw on that nice, beautiful curve. And there we go. That is that particular sine curve. And it would come back down, and we can just put an arrowhead on it and leave it be.